Let's begin a new topic, which is the ideas associated with thermochemistry, which is the study of temperature and heat. Energy in general is the ability to do work. One might imagine work to be like a steam engine, can move a train, or work is the ability to produce images on a computer screen. All these types of work require energy. And as you've indicated, energy comes in many types. There's what is referred to as radiant energy. Think of light. Think of electricity. Think of kinetic energy is like the steam engine or a baseball being thrown. Chemical energy is what is released during the detonation of dynamite. The final is potential energy, which is material storing energy that can be used later. The electromagnetic radiation is not a central topic of the course we have, but is one that needs to be kept in mind because a lot of chemical reactions do produce a radiation. As mentioned, kinetic energy has motion to it. The energy is stored in bonds, which is the idea of dynamite or gunpowder or any other type of chemical reaction taking place. And that is potential energy, which is the stored energy with it. Now, we need to make a very important distinction here, and there is a difference between temperature versus heat. We've discussed this in class, and it really needs to be made clear. Temperature is the actual physical random motion of the particles. And that random motion is therefore a measure of kinetic energy, since motion of material is kinetic energy. But temperature is a measurement of the actual motion itself. Now, heat is the energy that is being transferred between two objects, and that heat transfer can be detected in a change in the random motion. So in order to measure heat being transferred, you actually monitor the change in the temperature between two objects. So you'll notice in the example that the temperature of object A is greater than the temperature of object B. There is no heat transfer going on, so there is no change in the temperature. When in fact you create a physical contact, now the energy called heat can be transferred. What happens during the actual transfer itself? How exactly does the energy that's in the random motion of A increase the random motion of B? And the answer is most illustrated by billiards or pool, the game of pool. When you have the cue ball, which is in white at the top, it's in motion. You can think of it as having random motion, and therefore it possesses thermal energy. But that thermal energy needs to get transferred to the other ball, which is in purple. And the way the transfer takes place is there has to be a physical collision. And that's going to be a very important idea, because you can have a heat transfer only when you have a direct contact between the two objects. And here you can see why that's true, because I need to have a physical collision take place between the two billiard balls. When that collision happens, the white ball does work against the purple ball and sets it in motion. And by setting the purple ball in motion, we've now given the purple ball energy in the form of motion, and obviously the white ball that gave up its motion has lost some. So when you have, backing it up here, when you have a thermal transfer, which you see on the right, what happens is the physical contact point between item A and item B, at the point of contact, there are billions and billions of molecules of A slamming into molecule B. Those molecules of B were moving much slower, and we know that because the temperature was lower. But by having molecules A hit the molecules of B, molecule B start to vibrate quicker. They receive the heat energy released from the A at the point of collision, and because the vibration now gets greater for B, it now records a greater energy change. But there's been a transfer, so the original amount of energy or vibration of A becomes less as it transfers the energy to B, which becomes more. So A, from a thermometer standpoint, A cools down, B increases, and that transfer of energy is referred to as the transfer of heat, just like you see here in the billiard balls. Notice the kinetic energy of the white ball, and to begin with, becomes 0, and the kinetic energy of the purple ball becomes greater than 0 in the transfer. Now this is an illustration of what we just talked about again. Notice what you have is the purple is vibrating slowly. So if you took a thermometer and put it in the purple area, you would find that the temperature is lower because there's less vibration. If you take a look at the bottom area, those are the red objects, and those red objects are vibrating very, very quickly. And the result is you stuck a thermometer in there, that would be considered very, very hot. Now because there is a physical contact between the purple area and the red area, at the point of physical contact there are significant collisions going on. And at the collision is where the transfer of the heat occurs. And so yes, if there was a gap between the purple and the red, you would not see any transfer of heat energy because there would not be any physical collision. So take a look. We have the purple at the top. I'm reading down the list on the right. You have lower temperature object in purple. You have lower average forces of collision. Now what happens is the particles speed up when there's a collision with particles of the higher temperature object. This increases their energy, which of course is increase in temperature. And then the higher temperature object has a higher average force of collision. They begin to slow down when they have the collision with the lower temperature object, and there's a decrease in the energy from the red region. And so that transfer of energy is referred to as a transfer of heat. Now, the physical collision is not the only way that you can transfer the heat. You can transfer it through convection, which is the movement of warmer fluids which are less dense. They rise, they cool down at the top surface, they drop back down because they are now less dense, and you have this circular motion of the material inside the pot because you have changes in the density, which is changes in actually temperature. There is conduction. Conduction is the type we just discussed, where you have a physical intimate contact between two areas or two surfaces, and there is through collision there's a transfer of heat energy. That's the conduction type. And finally, radiation. Radiation is the emission of infrared, which we experience as heat on our skin. Now, when you have heat transfer, this is a really important idea. The heat transferred takes place between two areas. You have liquid inside the bottle. The area inside the bottle is referred to as the system. And what's going to happen is the outside of the system, the outside portion of the bottle, is simply referred to the outside environment also called the surroundings. And so what happens in all types of heat transfer is you have two regions, one the system, which is inside the bottle, and the outside, which is the surroundings. And heat is transferred in or out of the system into or outside of the system. Now in this given case, the bottle has open access to the outside. And because there's open access to the outside, physical material can move in and out of the bottle. And such a situation is called an open system. In the open system, physical material, is exchanged between the system on the inside and the surroundings on the outside. Now, a second setup is to put a cork in the bottle. And when you put a cork in the bottle, now there is no physical exchange of material with the surroundings. The system is sealed off physically from the surroundings. Now, you can and do have heat exchanges taking place because there is physical contact between the system, which is the bottle and the liquid inside the bottle, and the surroundings. So heat exchange does take place in a closed system. Finally, you have an isolated system. When you have an isolated system, material cannot move in or out, nor can heat. Notice that gray area surrounding the bottle. That gray area is a vacuum. And a vacuum prevents any physical contact between the material inside the bottle and the outside surrounding. If there is no physical contact, you cannot have any collisions. And without collisions, you don't get a transfer of vibration between the two areas. So there's no heat transferred, and therefore there's no temperature change. This is the basic design of all thermoses. A thermos is an isolated system, or it approximates an isolated system. It prevents the transfer of heat energy, either in or out, of the system by preventing physical contact. And so there are these three types of systems which influence the transfer of material between the inside of the system and the outside surroundings. Now, the word heat has a technical word to it, and the technical word is called enthalpy. And the enthalpy, or flow of heat, is given a value of Q. Q is a measure of how much heat has flowed. And as we just showed you, there are two areas that we pay attention to. We pay attention to the system, which is the inside area of any container, and we have the surroundings. And the question that is raised in thermochemistry is the amount of heat transferred between the system and the surrounding. When heat leaves the system and enters the surrounding, we say Q, which is the amount of heat, is less than 0. Now, that makes sense. It makes sense because if we are imagining ourselves to be standing inside that box, if we were inside the blue box, and we watched heat leave us, we would say, right, we lost heat. And so when the heat leaves the system and enters the surrounding, the Q value is given a negative. And the negative is telling you the direction of that movement of energy, which is out. Often Q is measured in joules or in calories. And when you have a system losing heat, the joule value will be negative. Now, what happens if heat is entering the system? One might imagine you have a coffee pot, and you put the coffee pot on the stove. The coffee pot is the system. Materials on the inside is what we're looking at. And the stove pumps heat in from the surroundings. In that case, the system's gaining heat energy, so Q will be greater than 0, and you'd have a plus joule or calorie count. And so the pluses and the minuses are representing the direction that the heat is flowing. And you need to pay attention to that direction, and therefore the sign, negative and positive, in your answer matters a lot. Now, when you have a endothermic reaction, we consider heat flowing into the system. So Q would be a positive there. So the Q of the system is gaining, and the Q of the surroundings is losing. In the case of an exothermic, the reaction, the heat flows outward from the system. Exo means release. And so as the reaction proceeds, Q of the system is negative because heat is leaving the system, and the surrounding is gaining that heat, and therefore the surroundings has a plus Q. In all calculations, in all the calculations of this unit, assume you are studying the system. So assume that when you run these calculations, it is based upon the system losing the heat or gaining the heat. So as already mentioned, enthalpy is the heat energy that has been transferred. Exothermic is the system is losing the heat, and the enthalpy is going to be greater than 0 if it is in fact endothermic. When you're on a sports field or anywhere and you get injured and they put a cold pack, in that case the endothermic reaction is the energy is flowing inwards, and the exothermic is when, for example, a flame is going. That is an exothermic reaction.